And we're back with Professor Stephen Williams of Southern Technical College, and we're going to go into Chapter 5 today with electric motors and talking about the motor principles.
All right, a lot of this is going to be a review to you at this point. Motor principles, we're basically going to say what makes a motor a motor. All right, a key thing that we need to remember is magnetism. Without magnetism, you wouldn't have a motor, okay? Electric motors are used to convert electric energy to mechanical energy. Okay, that's the important concept, okay? And when we're talking about efficiency, we're talking about how much mechanical energy that it takes compared to the amount of electrical energy you get out. They use magnetism and electric currents to operate. Keep it focused on there, okay, for the most part. All right, so if we talk about a permanent magnet, we've all seen them. We've got them a lot of different uses, a lot of different places. And typically it's a chunk of iron or whatever that's been magnetized. And typically it's iron or steel, or when such an object is near in contact with the magnet, it's attracted. Okay, a permanent magnet is able to attract magnetic materials because of the inherent magnetic force, which is referred to as a magnetic field. All right, so you can see here that here's your magnet. You've got two poles to a magnet, a north and a south. And the magnetic field of a permanent magnet is represented by lines of flux, and that's these lines of flux that are going from north to south pole, and that basically goes all the way around the entire magnet. It's shown two-dimensional, but three-dimensional. It creates like
a circle going from north to south.
Right. The stronger the magnetic field, the greater the number of lines of flux. And think of flux as a force field. Lines of flux are assumed to have a direction of movement from north to south, north pole to south pole, north being positive, south being negative. Okay, so with that in mind now, okay, let's talk about generators first, because if you get into generators, basically motors and generators are opposites of each other. In other words, one takes in mechanical energy to create electricity, and the other one takes electricity to create mechanical energy. All right, so they're just basically opposites of one another. And a generator, basically, you can see now we have a magnet that's passing through some coils, and you can notice by the ammeter that's on there, or the voltmeter I should say, that as it's passing through the coils, you can see that it's cutting lines of flux. The coils are cutting lines of flux and therefore generating power that's being seen on the voltmeter. Okay, a generator operates on a principle that a voltage is induced in a conductor whenever the conductor is moved through a magnetic field so as to cut lines of flux, or whenever the magnetic field is moved through the coils. Okay, they're both the same as far as the magnet could care less which one's moving. So an AC generator basically generates a voltage by rotation of a loop of wire. Okay, the rotating part is typically called the armature, and it's passing through the magnetic fields that are created, typically by coils that are surrounding the poles, the north and south poles. All right, and think of down here, think of this as a resistor that's coming off there, and you can see that it's creating alternating power, alternating current, and a sinusoidal wave. All right, so if we look at a DC generator, it's basically the same as an AC one. The only difference is we use a device known as a commutator, which is a split ring And essentially it's set up so that as it's passing through the 0 points on the curve, it's changing to a different segment on the commutator. And you notice as it goes through, it's changing. Okay, on this side, that's the AC that's being generated, but the output on the other side is actually little loops. Okay, all on the positive side. All right, so that's the purpose of the commutator, is to take them and flip them all up onto the top of the axis so that they're all positive. Now, as a form of DC power, yeah, that's not the best. However, as we've seen before, you can have additional coils in there out of position with one another. Let's suppose we've got 10 coils and each one is situated around there. Then we would have 10 individual loops all lining up there. And by the time you get there, you get to the point where it's darn near a flat line all the way across. So that's generally how a generator makes DC power. Okay, so we have a principle called electromagnetism. Magnetic field is also produced around a current carrying conductor. The strength of the magnetic field is directly proportional to the amount of current flowing through the conductor. So if I put more power to it, for example, if I've got a resistance associated with that coil, the higher the voltage I put to it, the higher the current's going to be. Okay, and the strength of the magnetic field is directly proportional to the amount of current. The shape of the magnetic takes the form of concentric circles around the wire. The relationship between the direction of current flow and through the conductor and with the direction the magnetic field creates can be shown using the left-hand conductor rule. Know that it exists. I'm not going to be testing on, because you and I have both sat there and played with it and you understand how we use it. You know, by the time you figure it out, well, it doesn't matter. Realize that if you change the direction of current, like for example, when you are involved with alternating current, it's continually 60 times a second changing direction. So as it's changing direction, it's also changing the magnetic field from plus to minus. It's like changing the poles from north to north to south 60 times a second. All right, that's what's actually happening inside there. So when the current carrying conductor is shaped into a coil, all the individual flux lines produced by each section of wire join together to form a large magnetic field around the coil. All right, again, this is going 360 degrees around that coil. The magnetic field produced by the current carrying coil resembles that of a permanent magnet. Okay, the difference being that you can change the strength of that magnetic field by changing the voltage. Now, why do you think that they use DC current in to change the strength of the magnetic field versus, DC voltage versus AC? Well, AC is continually changing, okay? On the other hand, DC is constantly the same. So you've got a strength that's coming out of that DC field that's staying only based upon, in other words, it's not going up and down like AC is, it's staying flat. So that you get a constant field strength. And that's great for producing power. So when you're talking about exciting a generator, you excite it with DC, all right? Because that way, the only thing you have to worry about is the voltage you put in. The higher the voltage, the higher the excitation. What's excitation? It's the current that's passing through the coil. Magnetic field of a wire coil is much greater than the magnetic field around the wire before being formed into a coil. and can be further strengthened by placing a core of iron in the center of it. Well, you remember you can have a core of air, all right? Air is, a core doesn't care what it is, but again, by wrapping it around something that is magnetic in nature, you strengthen that field tremendously, all right? Which is why typically your motors, your generators, your transformers all have ferromagnetic cores. So ferro meaning iron, okay, made out of iron. And as you remember before in our previous classes, we talked about the fact that we use plates, thin plates that we stack together. They're insulated from one another. And as we form those plates together, again, because it is a AC current that's currently going up and down, okay, you get what they call hysteresis inside there. You get things that are saying, wait a minute, I want to stay where I am. No, I'm getting pushed back and forth, okay? So they tend to drift out to the edges. And because of that, you get current flow going in through there, and you get a lot of heat loss. Well, if you make the outer surfaces very close to one another, there's very little flow. All right, so that's why they use plates that are insulated from one another and stacked together to form the core. So a motor stator is constructed using windings or coils of wound wire on an iron core. So when you think about the stator, okay, and again, we've talked about it in the past, a lot of times the power is going into the, most of the time the power is going into the stator. Now in a generator, the stator, most of the time, the magnetic poles are typically on the rotor for small generators, but those magnetic poles can move to the frame of the generator for the larger ones. Why? Because that's where you're pushing power out of the generator via those coils that are there. Okay, so looking at the picture here, a stator coils, you can see the coils of wire going around little poles in there, and your rotor, or the rotating assembly that goes through there, oftentimes called the armature, has conductors on there that are cutting the flux that's being created at these magnetic poles. So you can see that there's quite a few poles there. All right. Now, okay, so motor rotation. An electric motor rotates as a result of interaction of two magnetic fields. Okay, if we only have one set of poles, okay, one north-south set of poles, and an armature with north-south set of poles, again, the north-north is going to push away, the south-south is going to push away, and the south is going to be attracted to the north, and the north is going to be attracted to the south, which creates the force or the torque that a motor generates to be able to provide mechanical strength. All right, the electromagnetic is a moving armature part, and the permanent magnet is the fixed stator part. Okay, again, they can interchange as far as which is the rotating part. All right, depends upon where the bulk of the current is, because the bulk of the current is going to be large conductors, and of course, if all I'm doing is feeding excitation current in, I have to feed it in to the rotor via slip rings or commutators or whatever. But if I am feeding in to strengthen the magnetic field on there, that's a fairly small amount of current compared to the sometimes thousands of amps being generated, or maybe thousands of volts being generated, and associated current coming from the cutting coils. Because it's the cutting coils now that, okay, so sometimes those cutting coils are in the frame, sometimes they're in the rotor. Okay, so small ones, they're in the rotor, bigger generators, they're in the frame. All right, so don't assume that it's always one way or the other, because they're not. All right, so the electromagnetic is the moving part, armature part, and the permanent magnet is the fixed stator part. Again, can change. All right, like electromagnetic poles repel each other, causing the armature to begin to turn. After it turns part way around, the force of attraction keeps the unlike poles and becomes strong enough to keep the magnets rotating. Okay, so the rotating electromagnet continues to turn until the unlike poles are lined up. At this point, the rotor would stop, okay, because of the attraction between the unlike poles. Commutation is the process of reversing the armature current at the moment the unlike poles of the armature and the field are facing each other, thereby reversing the polarity, and now they're pushing away again till they get to the other part, and then the commutator switches it back and forth, and as it's switching back and forth, you've got a constant torque keeping them turning the entire time. Like poles, the armature and the field then repel each other, causing armature and rotation to continue. All right, when a current-carrying conductor is placed in a magnetic field, there is an interaction between the magnetic field produced by the current and the permanent magnet, which leads to a force being experienced by the conductor. In other words, everything wants to turn in there, right? Well, the current-carrying conductor, when placed in and at right angles to a magnetic pole, tends to move up at right angles to the field. Okay, so it's creating a force upwards. All right, one method used to determine the direction of motion of a conductor carrying the current in a magnetic field is the right-hand motor rule. Again, typical, your direction of motion of the conductor is the thumb. The direction of the magnetic field, north to south, is your pointing finger. And the force, okay, is your three fingers sticking out there, because I don't want to put one finger up there. All right, so the direction of current flow. All right, that's what's, and again, one method to determine the direction of movement of a conductor carrying current is in a magnetic field is the right-hand motor rule. Again, don't get hung up on that, okay? Just realize that it is something that changes as cutting happens, especially in AC current. It's constantly changing, okay? So that force is going back and forth the entire time. And it's happening so quickly that if we were to watch it, we'd never see it because our eyes aren't that fast. All right, the interaction of two magnetic fields causes a bending in the lines of force. Okay, when the lines tend to straighten out, they cause the loop to undergo a rotating motion. The left conductor is forced downward, the right conductor is forced upward. Okay, so you get that force on there, and that's what's causing it to rotate, right?
I'm not showing that rotation there.
And you can see the direction of the arrows is changing depending upon the direction the current's going. All right. A practical motor armature is made up of many coils. Okay, it is. I mean, you tear it apart. I don't like tearing them apart because they're paid to put back together again. However, a motor armature is made up of many coils. The magnetic fields of these conductors combine to form a resultant armature field with north and south poles that interact with those of the main stator field to exert a continuous torque. Again, let's go back. Okay. Down, up, okay. And when that happens, you get turn, okay? So, such is the way a motor works. In general, motors are classified according to the type of power they use. Two general classifications are AC and DC. Okay?
Not like the
Just two
band?
different kinds of power. Alternating and direct current. No, not like the band. Okay? DC uses permanent magnet, series wound, shunt wound, and compound wound. We're going to be getting into them in the next chapter, I believe. You also have a universal, which is kind of a cross between an AC-DC. Okay, you can use it, theoretically you can use it in either DC or AC applications. And then you've got generally AC motors, which are by far, they make up probably 90 to 95% of the motors out there. Not saying that DC motors aren't used. Well, in fact, there's a lot of applications, more all the time, I guess, with the electric cars that are coming out.
That's true.
And we've all seen the alternators and generators are in AC cars and in even the gasoline-driven cars. Okay, but generally, you've got either a single-phase motor. Now, when it says single-phase, it's got two conductors coming in, all right? That could be, for example, it could be 120 or 110, okay? And that could be a phase wire and a neutral. Neutral typically being grounded back at its point of origin. Or you've got polyphase, which polyphase is typically, you're talking three-phase, but you could also, because talking two phases of a three-phase system used to power a motor. If you don't need as much power as three phases require, you can use two phases. And again, phases, yeah, I don't want to go over it again, but it depends upon whether they're Y or delta wound, the relationship to the current and the voltage in the different windings.
And that we talked about in the last video.
That's correct.
So you can always review that if they need to.
Yep. Okay, so big picture, DC motors, pretty much the same as what we just looked at. Polyphase, we have motors can be broken down into induction and synchronous. And think of it as induction is something that has no brushes, okay, and makes up the vast majority of motors. All right, so you have single phase and multi-phase induction motors, and think of synchronous it is something that has voltage being supplied to the rotating element in there. So typically it has some type of either commutator or slip ring associated with it.
Now, under induction, I'm seeing squirrel cage. No, they're not really talking about a squirrel in a cage, right?
No, but it looks a lot like a squirrel cage, so that's why they give it that name. Okay, and you can see that there's a number of different varieties up there. Split phase is probably number 2, capacitor start for single phase motors. And again, we're going to talk about it a little bit. When you have a single phase motor, since you only have one phase and it's constantly changing, it's going to sit there and go like this, but it never really gets started. Okay, so it needs a way of getting started. Okay, getting spinning. Once it gets spinning, it's cool. All right, but getting it there is another thing. So split phase is one of the processes they use there. A capacitor start is another one. And then you've got permanent split capacitors. You've got capacitors start and capacitor run. You got split phase start, capacitor run. You've got shaded poles. There's all different kinds. All right, now, again, that's single phase. They're usually small horsepower motors. I don't think you'll ever see one over about 5 horsepower. A lot of times they're fractional horsepower, like 1/3 horse or half horse or 1/10 of a horse or whatever. And then the synchronous, you've got permanent magnets, but you have the capability of basically, believe it or not, controlling power factor. Because if you under-excite, okay, you're giving excitation to the coils, and if it has a synchronous speed. Now, if you have to excite it to get it to that speed. When you over-excite it or under-excite it, you can add or take away VARs, okay, which is voltage reactive associated with typical induction, all right? And you've got wound rotors. Typically the wound rotors, again, you're trying to feed power into a wound rotor. So you can have wound rotors that have slip rings on them, but again, the vast majority of them are induction squirrel cage. Okay, so, okay, moving on. That's it. Okay, so that's the end of the first part. We're going to do parts 2, 3, and 4. So we'll take a little break here and be back in a minute.